In mathematics, an incidence matrix is a matrix that shows the relationship between two classes of objects. If the first class is X and the second is Y, the matrix has one row for each element of X and one column for each element of Y. The entry in row X and column Y is 1 if X and Y are related and 0 if they are not. There are variations, see below. Graph theory. Incidence matrices are mostly used in graph theory. Undirected and directed graphs. In graph theory, an undirected graph G has two kinds of incidence matrices, unoriented and oriented. The incidence matrix G is a n times m matrix, where n and m are the numbers of vertices and edges respectively, such that if the vertex and edge are incident and 0 otherwise. For example, the incidence matrix of the undirected graph shown on the right is a matrix consisting of 4 rows and 4 columns. If we look at the incidence matrix, we see that the sum of each column is equal to 2. This is because each edge has a vertex connected to each end. The incidence matrix of a directed graph D is a n times m matrix, where n and m are the number of vertices and edges respectively, such that if the edge leaves vertex, if it enters vertex and 0 otherwise. An oriented incidence matrix of an undirected graph G is the incidence matrix, in the sense of directed graphs, of any orientation of G. That is, in the column of edge E, there is 1 plus 1 in the row corresponding to one vertex of E and 1 minus 1 in the row corresponding to the other vertex of E, and all other rows have 0. The oriented incidence matrix is unique up to negation of any of the columns, since negating the entries of a column corresponds to reversing the orientation of an edge. The oriented or unoriented incidence matrix of a graph G is related to the adjacency matrix of its line graph L by the following theorem. Whereas the adjacency matrix of the line graph of G, B is the incidence matrix, and is the identity matrix of dimension M. The discrete Laplacian is obtained from the oriented incidence matrix B by the formula: the integral cycle space of a graph is equal to the null space of its oriented incidence matrix, viewed as a matrix over the integers or real or complex numbers. The binary cycle space is the null space of its oriented or unoriented incidence matrix, viewed as a matrix over the two-element field. Signed and bidirected graphs. The incidence matrix of a signed graph is a generalization of the oriented incidence matrix. It is the incidence matrix of any bidirected graph that orients the given signed graph. The column of a positive edge has a +1 in the row corresponding to one endpoint and a -1 in the row corresponding to the other endpoint, just like an edge in an ordinary graph. The column of a negative edge has either a +1 or a -1 in both rows. The line graph and Kirchhoff matrix properties generalize to signed graphs. Multigraphs. The definitions of incidence matrix apply to graphs with loops and multiple edges. The column of an oriented incidence matrix that corresponds to a loop is all 0. Unless the graph is signed and the loop is negative, then the column is all 0 except for + or -2 in the row of its incident vertex. Hypergraphs. Because the edges of ordinary graphs can only have 2 vertices, the column of an incidence matrix for graphs can only have 2 non-zero entries. By contrast, a hypergraph can have multiple vertices assigned to one edge. Thus, a general matrix of non-negative integers describes a hypergraph. Incidence structures. The incidence matrix of an incidence structure C is a P times Q matrix, where P and Q are the number of points and lines respectively, such that if the point and line are incident and 0 otherwise. In this case, the incidence matrix is also a biadjacency matrix of the Levi graph of the structure. As there is a hypergraph for every Levi graph, and vice versa, the incidence matrix of an incidence structure describes a hypergraph. Finite geometries. An important example is a finite geometry. For instance, in a finite plane, X is the set of points and Y is the set of lines. In a finite geometry of higher dimension, X could be the set of points and Y could be the set of subspaces of dimension 1 less than the dimension of Y, or X could be the set of all subspaces of one dimension D and Y the set of all subspaces of another dimension E. Block designs. Another example is a block design. Here X is a finite set of points, and Y is a class of subsets of X, called blocks, subject to rules that depend on the type of design. The incidence matrix is an important tool in the theory of block designs. For instance, it is used to prove the fundamental theorem of symmetric two designs, that the number of blocks equals the number of points.